Okay, so this is lecture 8 of the Real-Time Digital Signal Processing Lab class at the University of Texas at Austin, spring 2014 semester. So we left off on slide 8-4, and we've done system properties of the process of analog to digital conversion. And in doing so, looking at the properties from last time, we filled these out, and this is in cascade. The cascade in total is nonlinear and time varying. So the cascade here, which is the theoretical view of analog to digital conversion, is nonlinear and time varying. So it's pretty hard to analyze. But the blocks are a little bit easier to analyze because we know the analog low-pass filter, provided initial conditions are 0, is LTI. The sampler is linear time varying. The quantization is nonlinear, but time invariant. So we can, and we do, and we have. We've looked at sampling in a lot of different contexts, filtering. So today we're going to dive into the quantizer a little bit more deeply. So we've done a few introductory slides on the quantizer. And the key takeaway today is to derive the signal-to-noise ratio at the output of the quantizer, which we'll see will be 6 dB per bit of quantization plus an offset. It's a very important formula. You'll use that one, I think, the rest of your career, dealing with any quantized data of any kind in any application scenario. So it's a very generic result. All right, so let's continue on the discussion here of amplitude quantization. So there are many different ways to do amplitude quantization. Here are two of them. Both are uniform. They're uniformly spaced. So there are a lot of applications for non-uniformly spaced quantization. That's beyond this class, but I'll tell you they are out there in practice. We use them in data conversion. We also use them in compression. Lots of context. All right, so in the case here, when you uniform quantization, and remember the A to D converter is in our receiver and in many systems coupled with an automatic gain control separate from the A to D converter. So it's another level of sophistication in the system, which can provide some interesting scaling of this quantization effect. All right, so let's do the quantizer in isolation for pretty much the rest of the lecture today. So two possibilities of many for uniform quantization. We have round to the nearest integer, and we have round with offset. Now the bottom one is the one we're going to use to derive the SNR formula for quantization. So just to kind of look at what happens. So I have an input X, think of it as a voltage. I have an output that takes one of a finite set of levels. Can't be infinite. It's not floating point anymore. It's not a real value. It's going to be from a set of quantized amplitudes. So the set I show you here is 1. As far as the quantized outputs, we have 1, 0, -1, and -2. Those are the 4 possible outcomes. If the input to the quantizer falls inside this range, where we have more or less a linear response, we call this the linear region of the quantizer, and we can approximate the input-output relationship with a scalar gain, and we'll do this in lecture 10 with data conversion. It gives some very nice analytical results because it converts a nonlinear system into a linear one by approximating the quantization output as a scaled version of the input. Okay, we'll do that at a later time, not for today. If we fall outside this, called linear region, if you will, then we get clipping. And so if X is greater than 1.5, we're going to clip. And so if X is 10, quantized output's 1. It's a hard rail. Now this clip is a big deal because if I get a lot of input that's above 1.5 for X, I'm clipping that to 1. So if I put in 10, my error is very large. Because my output's 1, my input was 10. It's a very large error. So we try to use automatic gain control in conjunction with an A to D converter so we keep the voltage levels in range of the quantizer, in this linear range of the quantizer. Otherwise, we get incredible clipping noise, and this is a real problem in systems. We want to avoid that clipping noise. It turns out to be, if you do the clipping noise has, roughly it's spectrally flat noise, but it has some other components, depends on the input. It's pretty devastating for a system to have a lot of clipping noise. All right, now so definition, the step size, delta, is really just this distance here. And so that is the step size. Now you can compute the step size pretty easily by looking at the max voltage minus the min voltage divided by the number of levels, minus 1. Right, the number of steps that I have here is the number of levels minus 1. I have 4 levels, 3 steps. And so if I do that math, I get 1 minus a minus 2, which is 3, divided by 3, which is 1. Right, so the step size here is 1 volt for this particular example. But it's uniformly spaced amplitude values. The next step is to encode these amplitude values into a binary pattern. And we can use we have another degree of freedom here. We don't have to go with a 2's complement or any other version. We can just encode however we like. Now, it is common to try to encode this in a 2's complement way so that when we do mathematics or arithmetic on the quantized output, it has a mapping back to voltage. All right. So here's one possible mapping. You can say, well, we'll represent the levels from bottom to top. It almost doesn't matter here. This way, right? Or we can do it this way. Now, if we do it the second way, that should be a little familiar. So I would have mapping would be 1, 0, 1, 1, 0, 0, 0, 1. What does that mapping look like? It is not gray coded because I have 2 bits changing from 1, 1 to 0, 0. Okay, but what is it? Remember, I'm trying to map the quantization levels, which is 1 to 0, 1, 0 to 0, 0, minus 1 to 1, 1, minus 2 to 1, 0. It is 2's complement, okay? And it's right there. All right, so it is 2's. Yeah, often I do this. I ask the question, and the answer is somewhere on the slide, or one slide plus or minus happens. Yeah, so this is a 2's complement encoding, but again, you don't have to use a 2's complement encoding, right? But you can. And we do. It's a common one if we want to do arithmetic in 2's complement with the output. So it's a pretty common encoding. Okay.
Why do we want to do that? Like, what benefit represent 2 complement?
Well, now we can do all the math we want. We multiply, add, and it's very easy.
We're saying we're just doing this just for the benefit of the software.
One benefit is software. The second benefit is it cleans up noise. Okay, so the good news, there's good news and bad news. The good news is we remove any noise less than half a step size, plus or minus half a step size. The bad news is, because of quantization, we introduce quantization noise, which is even greater than the noise we cleaned up. Okay, so there's a trade-off in how much quantization noise are we willing to introduce in the system. This becomes our new noise floor in many cases. It's more noise than thermal noise. The ideal case is to match the quantization error with the thermal noise, be right at the noise floor, and then we don't add any noise to the system. That's nice when we can do it. But the main thing is just convenience. It just allows us to do inexpensive calculations. Now we can do everything in discrete time and digital, take advantage of Moore's law, programmability, configurability, easier to update, upgrade, fix, maintain. Now, the other version I have down here on the bottom is also amplitude modulation, uniformly spaced. And here the rounding is with an offset. And so I don't exactly represent 0 anymore. So now if I look at the input-output relationship, my quantization levels are now at half point. So I have 3 halves, 1 half, minus 1 half, and minus 3 halves. Okay, so there's flexibility. Now in the derivation, we're going to use this mid-rise quantizer, this rounding with offset, to derive the SNR formula for quantization noise, given the number of bits. So here it's a 2-bit quantizer, 4 levels. Right? And again, so I'm just changing where the thresholds are happening, right? So if if I'm between 0 and 1 on the input, so if X is between 0 and 1, then I'm going to end up at a half volt. And you can kind of eyeball this saying, well, my quantization error is, worst case, it's when I put in X is 0 or something very, very close to 0, I get a half. And when X is 1, I get a half. Okay, so the quantization error that results here is between a minus half and half. Another way to think about this is the step size is still 1 for this example, and the math is here. So there's your step size of 1. It's max voltage minus min voltage. So max voltage minus min voltage divided by the number of steps. Number of steps is number of levels minus 1.
What would the output be if your input is right where the quantize goes vertical?
Yeah, so you have to pick. Yeah, so when you're at a boundary, you've got to kind of pick it. So you got to be consistent. So you might say, I'm going to map 1 up here. I'm going to map 0 here. I'm going to map minus 1 here. I've got it included in one place, but not more than one place. So it's up to you. So look, in the end, it's a comparison. So do you greater than 0 or greater than or equal to 0 in the end? Okay. Again, there's a fast way to do the comparison. If we do this simply looking at the amplitude, the voltage x that comes in, divide and conquer, right? Compare x against 0, then compare x against 1 to narrow down which level you want. And you minimize the number of comparators in that particular design. But the trade-off is I now have longer delay to get to an answer. So it's a one way to do the conversion, I suppose, in analog circuitry. Remember, the amplitude here is analog. And the quantizer typically is clocked, so it's kind of discrete time analog. Right? The input is analog. The output's digital. That's the whole point of quantization. We're quantizing the amplitude. Okay, so keep this mid-rise in mind. We'll need it, later on to derive the SNR for the quantization noise. So now the next question is overflow, and this comes back to quantization because there are lots of ways I can handle overflow. And if I kind of just do, this is just two different ways to do it on a processor. And more commonly, we've used two's complement, and we still do. And that's true in the digital signal processor as well. So consider a set of integers, -2, -1, 0, and 1. It's the same set we had on the previous slide. And we're going to encode them in two's complement. Right? So the most negative number becomes, 1, 0, -1. It's always all 1s in two's complement. 0 becomes 0, 0, and 1 becomes 0, 1. So this first bit's the sign bit, right, for the two's complement encoding. Now, lots of ways I can add numbers together, and probably the standard way we're used to in two's complement is wraparound. So if I add, so if I think about, we normally do in two's complement, if I add -1 and -1, that's going to give me -2, not a surprise. If I add -2 and I add -1 to that, well, now I'm out of range of my representation. So what do? One answer is, well, I wrap around to the other side, and I call it 1. This is a two's complement way. Now if I add 1 to that, I go back to -2, and if I add 1 again, I go back to -1. And that's the right answer. Right? So that is the correct answer for this expression in exact precision arithmetic. So two's complement has the advantage that if the answer lies in the range of our number system, then we'll get the right answer. However, in two's complement, if the actual answer is not represented by one of the numbers in our collection, our finite set here, we'll get a different answer. It won't be the correct answer. Because we'll get wraparound. We'll get the wraparound answer, the modulo answer. We won't get the exact answer. Okay? But that's okay. So for a lot of things, that's okay. Now there's an alternative, which is saturation arithmetic, and this is on your digital signal processor. There are two different add commands. One is add, one is sad. And the sad is saturate. I know, I'm sorry. I didn't choose it. So it's saturating add, right? And there's saturating subtraction. So by default, it's two's complement. So for saturating subtraction, we do -1 plus -1 gives us -2, so that's fine. We then add a -1, and we take the quantizer approach from the previous slide. It's a hard limit. We don't allow wraparound. So anything at -2 plus -1 gives us -3. That's going to hit one of the rails. And that's going to be -2. That's saturation. Then we add -1 to that. So we add 1 to that, we get -1. We add 1 to that, we get 0. That's not the correct answer, right, from the exact precision calculation of what I have up here. right? This should be -1 in exact precision. Very simple addition. Right? Okay, now that doesn't mean that, again, they each have their limitations. Now, when to use it? So saturation is kind of this following idea. If the input value is greater than the maximum, then we set it to the maximum. If it's less than the minimum, we set it to the minimum. So this is exactly the quantizer view of things from the previous slide. And so, yeah, so this has a place. It's used in not just quantizers. We also tend to use it in implementing filters and other signal processing operations. We tend to prefer saturating arithmetic when it's available because what we really care about is how strongly am I responding to an input. Is it strong or weak? And if it's really strong, then we'll saturate to some value. And if it's really weak, then it'll be something close to 0. Okay, so in signal processing, we tend to go with the saturation arithmetic. Or if we do the wraparound, then what we then have to do is scale all the calculations so we don't go outside of the range of values, which reduces our resolution in the amplitude domain or an amplitude. So there's some downsides to that. Okay. So again, so when do we use wraparound? Well, certainly we want to use it for, it's going to be, again, what is it? It's addition performed modulo set of integers. And it's going to be, definitely we want to use it in calculating addresses. Given a base address and an offset, we want to use 2's complement. That's the way we want to do it. Now, and there are other cases you might use it, in simple operations, I don't know, perhaps hashing or something. Lots of ways you can use the 2's complement wraparound. But for signal processing, we tend to prefer saturation if we can do it. And a lot of general purpose processors, even going back to the mid-90s with MMX, 96 has support for this saturation. So you can find it even on, it's not just for embedded, standalone processors. Now in lab, it's mostly C code and it's whatever the compiler does, but you should be aware of what's going on. And we're in floating point in lab, so this is not really an issue for us. Right? We just scale the floating point value as we need to. But if we go to fixed point implementation, then you have to start worrying about these issues. All right, let's go back to the big picture for data conversion. This is the theory of it, not how we implement typically. It used to be done this way in discrete components, and occasionally it still does when the sampling rate's low enough and the quantized number of bits is low enough. So it does happen occasionally, 3 different blocks put together. But more commonly, we don't do it this way. And for audio codecs and for Wi-Fi or for cellular LTE, we wouldn't do it this way. But this is a good starting point for theory. So we've talked about this example a lot in audio CDs. Right? So this is standard 1982 Sony Philips. Introduced this, and for us, we mainly see this as MP3 files today. So it's going to be an analog low-pass filter followed by sampling, followed by quantization, and for the audio CD, it's 16 bits, per amplitude value that comes out of this quantizer. Pass band corresponds to normal hearing. Again, there are people that can hear outside this band. The analog low-pass filter is going to be low-pass with a 10% roll-off in the transition band. So 10% of 20 kilohertz is 2 kilohertz. So our transition band is from 20 to 22 kilohertz. Our stop band frequency is at 22 kilohertz. We've talked about this many times. Now, the choice of pass band ripple and stop band attenuation is now going to be a function of the number of bits that we want to have at the output of the quantizer. Okay, and we'll do the stop band formula now. I'll do the passband formula during review for midterm 2. All right, so this is what we're going to derive today. The signal-to-noise ratio when quantizing to B bits is the following. It's going to be, and this I'm giving you 3 significant figures. I don't remember this to 3 significant figures, but I'm going to give it because we'll derive it. So what is it? So it's some constant, depends on the application. Well, it depends on settings of the quantizer, honestly. In audio, this is 1 to 2 dB, roughly. In communication systems, it might be 4 dB. Just depends on different settings. Some constant. And then there's this term that depends on the number of bits, B. So it's 6.02 dB per bit. I never remember the 02, but I certainly remember the 6, right? 0.02 isn't very much compared to 6. It's pretty rare that 02 is going to really come into play. Even with 16 bits, the 0.02 is 0.3, 0.32, not much. So 6 dB per bit is what I hope you remember. One of the few things that I hope stays with you in your career. It's something that I use every day. You probably will too if you stay technical. So it's 6 dB per bit plus some offset. And this is, we're going to derive this, but it's a loose upper bound. It's not, it's more SNR than you really will get or need in practice or get in practice. Go ahead.
Is this SNR supposed to be like the SNR that we're getting when we're recording the actual like audio to the compact disc?
Correct. So the question is, what is this SNR? This is the signal to noise, but the noise here is the quantization noise.
So that's the only one.
That's correct. And the thinking is that we want to pick the number of bits to match the actual noise environment. We would like to match the thermal noise with the quantization noise. Because if we don't, if the quantization noise is less than thermal noise will overwhelm the last 2 or 3 bits, whatever it is of the quantization. They become unreliable, noisy, whatever. If the quantization error is noise is above the noise floor, then we just introduce noise to our system. But at least it means all of our bits are good in the quantization. Now you can work backwards from this, because this works for any SNR. So if I think about this from pulse amplitude modulation, it turns out the formula is the same. So if I know in my SNR, and you asked me earlier, where do I measure signal-noise ratio? In a communication system, almost anywhere. But in terms of where we do the performance plots, we tend to do it after the equalizer, if there's an equalizer in the system. But we can do it with any SNR to get probability of error versus SNR. If you're on video, you have to move forward to lecture 13 and 14 for pulse amplitude modulation for this background. Yeah, so you can work backwards with this formula or forwards. So if I give you the number of bits, it tells me what the SNR I can achieve. If you know what the SNR is, you can work backwards to find out the number of effective bits that I can use in my representation. So if I tell you the channel is, give you an example. So if I tell you that I have 8 bits in my quantizer, then 8 times 6 is 48, and then maybe plus 2 dB. So I get about 50 dB of SNR, or probably less than that. It's an upper bound. Probably a little bit less than that, but I won't be more than 50. Or if I tell you the SNR in the channel, let's say I measured the output of an equalizer, is 50 dB, how many bits can I handle of PAM? 8, but no more. So it works both. Man, this is one channel of quantization. That's what PAM is. PAM in the end is one channel. It's one dimension. 6 dB per bit works for PAM just as well. So it's the best we could do. So if we were to do PAM over a channel with 50 dB with this offset of 2 dB, the best we could do is 8 bits. Now in practice, we'll probably back that off and do 7.
Which one to do QAM?
QAM, actually, there's 2 channels. So it works out to be 3 dB per bit, and that was in homework 6, last problem. 3 dB per bit, 2 channels. That's why it's less. And this offset in QAM is about, well, the problem you had, this offset was 4 dB in homework 6. Okay, so 3 dB per bit for QAM. Another reason why QAM is a big win over PAM. All right, so if I have 50 dB in my channel, I can either do 8 bits of PAM or I can do 16 bits of QAM. Yeah, so it's a big difference. Now, this formula is more accurate as B increases. Right? So once we get to 16 bits for example, audio CD format, we're really close to what we can actually get. We're really close. But 98 dB would be what we actually would get from the formula for audio CD, and we really get about 95. So it's pretty close. Remember, it's an upper bound. this formula will give us a higher SNR than we can actually achieve. But it gives us something to work with, right? This is, a little higher than we can achieve. All right, now let's get to the stop-band attenuation specification for an ADD converter for a number of bits that I want to use in my quantization. So we'll go back to the concept of what's called dynamic range. And this is really, for us it's going to be SNR for this particular case. We're trying to design an LTI system, or analog anti-aliasing filter. So let's go back to basics. So the SNR, signal-noise ratio in dB, is simply, since it's in terms of power, it's 10 log 10 of signal power divided by noise power. And if we use properties of log, it means, well, this is the SNR, this is the signal power in dB minus the noise power in dB. Right. Again, it's the property of logarithms. And why is it 10 log 10? Well, if we think about, normally we use 20 log 10, but that's for amplitude. So if I have an amplitude A, normally I convert to dB, which would be the normal case for filter magnitude plot, magnitude response plot. If we know that power is, remember that power is proportional to amplitude squared, then if we use 10 log 10 of amplitude squared, then this just becomes 20 log 10 of the absolute value of the amplitude. So it's completely consistent. You just have to know whether the quantity is power or amplitude when you're converting to dB. Now, for linear systems, the dynamic range is just equal to the SNR. And when we think about how does this apply to filter design, when we want a low-pass anti-aliasing filter in our data converter, in our analog-to-digital converter, the anti-aliasing filter, the pass band is going to be at 0 dB, linear units of 1. And the stop band will be some much smaller value than 0 dB. That much smaller value is basically the noise floor. In other words, we want that stop band attenuation to match the background noise, whatever that background noise is. Okay? Now for us, we know what that background noise is because after the low-pass filtering and sampling, we have quantization. So we know that at the output of the quantizer, the noise power that we're ultimately going to have in our system is, the SNR here, because the SNR is already 0 dB. So here's the signal power. So that's our full scale. It's our signal power. And the SNR, so how do we get the stop band attenuation? We just subtract off the noise power, which in our case means that our stop band attenuation has to be at 98 point, or roughly 98 dB, down from 0 dB. That's a lot of stop band attenuation. From filter designs, this is going to be a very high order filter. Very high order. Okay, now let's talk a little bit about what SNR values mean and what kind of dynamic range 98 dB is. It's a lot. It's pretty amazing. So again, this is a slide from my first PhD student, Thomas Kite, and when he lived in Austin, he used to get a lot of phone calls from ESPN because the pro golfer of the same name lived here. He should have given an interview, but he never did. All right. So the anechoic. So if we look at what happens, there's a mapping from. Again, this is his slide. I'm not an acoustics person. I just, dabble, enjoy acoustics when I can. So this is his slide. So we have a reference dB, which we have reference sound level, which is basically 1 dB is 20 micropascals. So for those who know acoustics, this has meaning. For me, it's another unit that I can use in calculations. Either way you go with it. All right. So what do I know? I know that given this reference of 20 micropascals to mean a dB. 40 dB is the signal pressure, the sound pressure level in a typical living room, dorm room kind of scenario. Dorm lobby may be louder, but all right. And what's the threshold of pain? Well, 120 dB normally. So this gives you an 80 dB of dynamic range between the background acoustic noise and the maximum sound you could play out over speakers without, being in pain. So the best you can do is 80 dB. Now, if you happen to have essentially a soundproof chamber, an anechoic chamber that absorbs, it has foam on the walls and arranged by cones in foam all along the walls, so all the acoustic waves are absorbed in the walls, and almost nothing comes back in reflection. The background noise is about 10 dB. So if you have an anechoic chamber or have access to one, then the dynamic range of an audio CD isn't enough. You'll hear it isn't enough for the dynamic range, because in the case of anechoic chamber, the dynamic range is 120 minus 10, so it's 110 dB, which is way more than you can get with the audio CD. Okay. So for very loud sounds, audio CD is enough. 16 bits is enough. Now, where do we have problems? Where do you think we're going to have problems? We're okay with loud sounds. Where's the problem? Quieter sounds. Because when it's very quiet, I have very few levels to choose from. I have severe quantization effects when the track goes from very loud to very quiet. Maybe I'm down to just 2 or 3 bits of what I can represent when it's really quiet. That's all I got. Good.
Is that why louder songs are perceived to be better? Because you have more.
To a point, that's right. That's right. And I think there's been in the last 10 years, a lot of extra loudness engineered into pop songs. That's correct. For that reason. So actually, Dr. Kite has he works for Audio Precision, which is a pro audio test and measurement company. So he removes that loudness that's engineered in. It's about 9 dB. He just removes it from his music before he listens to it. Anyway, go on.
How are we differentiating? I just thought you saying that made me think about this. How are we differentiating between like the bits that represent the audio, and then there's just with any audio system you're going to have just a raw gain that will multiply, it will either attenuate or increase the volume. So like, you can still represent a range of sound and still have a low volume. Are we like?
Yeah, the question is, what do you do with like volume control, and there are other things like power amplifiers and so forth. So you have to have other parts of your system compensating. So when you design an amplifier system, you're going to design, if you are wanting to spend some money on the speakers, there's going to be some counterbalance, some equalization, some crossover design to give you a good flat spectrum when you play it back. So you assume that the audio equipment you have doesn't have a lot of distortion across the audible band. So higher end, a good equipment will try to avoid that. When the user cranks up the volume, you do face less ability, right, to a point. So if it's really quiet, you have almost no ability to represent it, right? So if you think about turning the volume way, way down and listening to the speakers, you're hearing very few levels when the gain's way down. When the gain's way too high, you're just getting, it's just loudness, right? So there's some point where you want to have the volume control comfortable so you can hear the range of the music, and that's something you pick. And there's also the stereo system has its own effects that you can pick to enhance the playback. You can mimic a concert hall, which is a convolution effect of the impulse response of a concert hall. And you obtain that impulse response by a pseudo-noise sequence, sent it over speakers and picked up by microphones in the hall you're trying to mimic. So so another pseudo-noise application. But so there's a trade-off when you crank up the volume, absolutely. But other sorts of distortion, like power amplification, is supposed to be, or splitting between woofer tweeter and subwoofer. The audio system is supposed to handle compensating for the distortion that incurs, usually in the box itself. Okay, let's go ahead and derive now a formula for 6 dB per bit. And we're assuming that the input to the quantizer is what we want to represent. Okay, so we assume that that's our signal. Even if it has noise, we don't care for this derivation. So that's our signal. It's our message, if you will. So we have an input signal. So the quantization output will be this input signal plus noise. Right? So the output will be essentially the input plus some random offset to make it to one of those quantization levels. And the noise here is the quantization noise, and this is the difference between the output and the input signals. There are a lot of assumptions in getting this formula. Okay, so one of the assumptions in getting this formula is that the noise, which is the difference of output and input, is statistically independent of the input signal. Okay, so that is, you know, and in practice uncorrelated. Well, not so much in practice. But again, it's an approximation, it's an assumption we're going to use to get to this formula. There's another approximation coming, so these are just good to keep in mind what are the limitations of this approach. All right, so we're going to quantize to B bits. And this is true in general. Whenever you have a signal-to-noise ratio, there's an implicit assumption that the signal and the noise are statistically independent. And in practice, they rarely are. And the question is, how much are you, you know, it's just an approximation to get going on derivations. But the correlation between the two will usually reduce your results. Lower your upper bound, raise your lower bound, whatever. And that's why, it's one of the reasons that the upper bound isn't reality. The upper bound is beyond reality, right? It's this case where we're assuming independence, statistical independence. All right, so we quantize to B bits. The quantization error is simply the output minus the input, and we'll represent this as a random number with a particular distribution. So another assumption, we'll assume that we have a mid-rise quantizer, so it's symmetric in dynamic range, positive and negative voltage values, and that we're in the linear region. That is to say, the input doesn't overload the quantizer. We're not being clipped. We're not out on the extremes of the quantizer input-output plot or relationship. We also assume that the quantization error is uniformly distributed. Now, this one is defensible because if we assume that the input values, so if we assume that if the input values fall in the linear range of the quantizer, and we further assume that the values here of the input are equally likely to occur, then from that it follows that the quantization error is uniformly distributed. And I gave you the example last time of, so if you just take a 1-bit quantizer, it's mid-rise. And I'm in the linear range. So here's half, here's minus half. So if I'm in a linear range, so if I put in, let's say I put in one volt, the error is a half. I put in a half a volt, error is 0. I put in 0, and the error is, so actually here the error is minus 1/2 if I put in 1 volt, right? It's output minus input. If I put in 1/2, the error is 0. This minus 1/2 is the level here, the bottom level. And if I put in, say, 1/4, then the error is 1/4. I put in 1/8, etc. So that if I'm uniformly distributed from 0 to 1, or from minus 1 to 1, when I fall in the range 0 to 1 on the input x, that quantization error is plus or minus 1/2. It's plus or minus half the step size. And if x is uniformly distributed, then the quantization error will be uniformly distributed from minus 1/2 to half in this case, or more generally, from half the step size, minus half the step size to half the step size. We also assume the number of quantization levels is large, and you'll see why that occurs in just a second. So this is saying that the number of levels, which is 2 to the number of bits, is large, because later we're going to make the following approximation that 1 over quantity L minus 1 is approximately 1 over L. So when B is 1, say B is 1 bit, 2 levels, I'm trying to convince you what? That 1/2 is approximately 1. Does that bother you? Bothers me. 10% error, I'm all about. We're all about as engineers. But so when levels are really low, this bound is really off. So for 1 bit, this formula is way off the correct what's achievable. All right, now this I'm not going to have to go over because for those on the video, we did this out of order. So we did this in lecture 13 slides on the match filter. I don't remember if it's 13 or 14, but it's the match filter slides. And we did this in great detail. So we won't have to do this here. All right, so let's continue on with the derivation. So the step size is going to be the range in voltage divided by the number of steps. So number of steps is L minus 1, and this is where the approximation comes in. So I'm going to approximate 1 over L minus 1 as 1 over L. Quantization error is uniformly distributed from half the step size to minus half the step size, or from minus half the step size to half the step size. So this quantization error is the sample of a zero mean random process, capital Q. Q is uniformly distributed. The mean is 0. Average value is 0. The variance, which is going to tell me the amount of noise power, right, is just the expected value of Q squared minus the mean squared. Luckily, the mean squared is 0. So that goes to 0. And I look up what this is for the uniform distribution probability book, and I get that it's it's delta squared over, it's a step size squared over 12. And I can replace what I know about the step size into the formula. And now I get the variance is a function of the maximum voltage squared and an exponential function of the number of bits. Okay, remember this is in linear units, it's not. We haven't done any dB yet. Okay, we'll look at the SNR here. It's signal power over noise power. I don't know the signal power. I know the noise power. I don't know the signal power. So we're going to let the signal power be a placeholder. And we'll do this in terms of average power for the input. And then we can put in the rest of what we know for the noise power, which is just the variance. And now we have an SNR that now starting to look interesting. We have a bunch of constants times an exponential, and this exponential is exponential in the number of bits. So that if I, double the bits, I get a huge, so if I add 1 bit, I get an increase in the SNR in linear units by a factor of 4. So in other words, SNR is exponential in the number of bits. This is huge. So I add a bit, I get this massive increase in SNR. So that's a good thing until we hit the thermal noise in the system. So there's a caveat. We just can't keep doing this until B is 1,000 or 1,000,000 or something. All right, to get this into dB, all we need to do is convert SNR into dB. SNR in linear units to SNR in dB. So just take 10 log 10 of what I had on the earlier slide. And properties of logarithms come to our aid here. So we just, every time we multiply in the argument of the log, we're going to add the logs together. We divide, we're going to subtract. And so what I'm left with is a whole bunch of constants. And this depends on the max voltage, M max. It depends on the average power of the signal going into the input to the quantizer. So M max is a quantizer setting. It could be 3 volts, 5 volts, whatever it happens to be. And the average power of the input signal is somewhat application. It is application dependent. So there's some constant, and again, this constant could take all kinds of values. In audio, it tends to be between 1 and 2 dB. What matters more, though, is this, is that we get 6 dB per bit. And that simply comes from the log. It's 20, it's a log, 10 log 10 of 2 to the 2b. Properties of logs, the 2b comes down to scale log 10 of 2, and that's where the 6.02 comes from. The 6.02 is the log base 10 of 2. That's where the value comes from, times 20, times 20. And again, so some questions here. So what's the maximum number of bits of resolution? So if I tell you the audio CD signal has an SNR of 95 dB, and you work backwards from this, how many bits do you get? You almost get 16. Well, but I'm telling you it's 95. So I'm telling you the actual SNR in practice is 95 dB. How many bits does that really correspond to? 15 and a half. If we let this constant be 2 dB, right? To make sure I've done that correctly. So 15.5 times 6, 93. Yeah, I'm good. All right, this is for, so we call this constant C naught, and this is for C naught equal to 2 dB. Now, it means that that last bit isn't entirely reliable.
Why don't we just say 15?
You can, but it's really 15 and a half. So it's 15 good bits, and then that last bit is got lots of noise in it. Now, on your board in lab, that you use in the lab component, you look up the spec sheet on this, and it tells you that the analog to digital converter has 90 dB of SNR. And so you run the formula on this, and you get 14.6 bits. Now, you've been reading 16 out of this thing for all lab, but guess what? You got 14 good ones, 14 good bits. The 15th bit is okay, and the 16th bit's a bunch of noise. All right, now, the good news is we'll talk about the DAC, it's a little bit better. Now, there's another type of measurement called total harmonic distortion, which I have a slide on coming up next. So that's 80 dB, which means you really have 13 bits. This is if you input just a single tone, how much accuracy a tone at 1 kilohertz, how much accuracy do you have? 13 bits. So it's not even as good as 14. Go ahead.
So then the 14.6 bits is only due to quantization error.
Correct. So but it tells you that, yeah, so the spec sheet tells you that the SNR range is 90 dB. So you can now work backwards to find how many good bits do I have. Now, but the total harmonic distortion tells you even more. You really have 13 good bits. You should feel really good about those first 13 and not feel so good about, 14, 15, and 16 bits.
The THDs do all the other non-idealities.
Correct. That is correct. That is correct.
So are these bad bits on the MSB side, so like the higher data?
No, lower. They're on the least significant bits. So the upper 13 bits are good. The least significant 3 bits, not so much. Right? Not so much. But what are you going to do? Read 13 bits? I mean, we work in, groups of 8 bits, right, in bytes. The digital to analog converter is a little bit better, and that has 100 dB of SNR range, so 16 good bits. It's a good sign. Total harmonic distortion, okay, not as much. You get 14 good bits. And I gave you the page numbers where I pulled that from.
So the automatic gain controls are factoring this into how much gain it's going to apply, because you want to put more of your signal in your MSBs, right?
This is, okay, so this is telling you that for a certain test signal, they measure the SNR, so send pseudo noise through, and they measure the SNR that comes out, because they know what the input signal should be. And I'll give you the measurement for total harmonic distortion next slide. That will help, I think, a lot. So the test signal, so this is just from a test signal. Both of these measurements are from a test signal. Let's talk about total harmonic distortion. And believe it or not, this will come up Cirrus Logic. You nailed it. So there was a student a couple years ago that got a job from Cirrus Logic on this lecture. She just nailed all the questions that they asked, including this one. She got the job, got the internship, and then that led to a full-time position. Total harmonic distortion. So it's a measure of pretty much all the nonlinear distortion in the system, due to quantization, whatever, all kinds of effects. The test signal that we're going to use is an input. The input is going to be a sinusoidal signal of a fixed frequency. And for audio, we tend to use the sweet spot of human hearing, which is at 1, remember this? 1 kilohertz. Very good. You'll do well in an interview. This is good. Feeling good. I want you to do well in your interviews. All right. So you can look at, so I put in a sinusoid of fixed frequency, and from the output of the system, I subtract off the signal that I know, which is the input signal. And everything else that's left over is all the other stuff that whatever that system created. And then I take an SNR measure. So in audio, let's see how we're going to do this. And again, it's good to have the answer at hand. Go ahead.
Take an SNR measure. If you're subtracting the input signal, what's
Right. So the signal is the sinusoid, and the noise is everything else. All right, so let's talk about this on the bottom block diagram. So here's an example. The system we want to test is an analog to digital converter. That's here. We have a calibrated DAC, D-to-A converter. The signal is x of t, which is going to be our 1 kilohertz sinusoid. We're going to put that through an A to D converter, and this is going to be the same sampling clock is feeding the A to D converter, right, and the D to A converter. So they're synchronized automatically. So I feed in this 1 kilohertz analog continuous time signal. I go through A to D conversion, go back through D to A, and I assume that I've already got a good calibrated D to A. And we already know that from previous slide that D to A is better, has more accuracy than A to D in general.
If you have multiple converters like that, where you have A to D, D and A, and each of them has their own SNR. When you're considering the SNR of the whole thing, do you just say I'm going to limit it by whichever one has the worst?
So the question, I'm going to, yes. The question is, do I limit? If I remember, the system under test is the A to D converter, and I'm testing it with components that are more accurate than the A to D converter. Remember, a DAC has more bits, can represent more bits than an A to D for the same. Yeah, no, in general, it's the worst case. You look at, I mean, it's like the weakest link in the chain, that same analogy, right? It's the weakest part of the system. All right, so we calibrated DAC, right? So what happens? We put the 1 kilohertz signal, 1 kilohertz analog continuous time through the converter. So what happens? We have to set the delay right. Always got to set the delay right to match the delay. And we can, how do you estimate the delay? Pseudo noise, good. This is good. So I have to, before I do this, I send pseudo noise through, and I do correlation to figure out what's the delay through the A to D to A. Okay. All right, fine. I can also even do it for this particular test signal. I can separately calibrate for that frequency, figure out what's the delay that I see on the output. Correlation. All right, fine. So I got a delay. It's a fixed value. And now the difference is the noise. This is all the other stuff. This is additive noise in the system. This is nonlinear distortion of the 1 kilohertz sine wave. This is everything else. You can do this for any blocks. This is a fairly general test. But again, your test equipment has to be more accurate than what you're testing, right? So a company like Audio Precision that I mentioned earlier does this stuff. National Instruments. There's a number of companies that are in this space. And so the SNR would be the signal power in X divided by the noise power in N. And that's your total harmonic distortion number. And I'm going to skip that slide, but I'll let you read that slide is important, but we are out of time. But I will give you the summary of that last slide. So what did we do in the quantization lecture? We did amplitude quantization by approximating its input by a discrete amplitude taken from a finite set of values. We derived a loose upper bound in SNR in the signal noise ratio of a uniform amplitude quantizer with an output of capital B bits. Best case, upper bound. Practice will be less than this, but the upper bound is 60 dB of SNR gain for every bit added to the quantizer. And a key limitation, we assume that we have a large number of levels to make that. And so the larger the number of levels, the more accurate this 60 dB per bit formula applies. I skipped the slide, but I do want to cover it quickly. Go back to 8-16 to cover it in more detail. If we look at noise immunity, which is a measure of communication system performance, in analog, it's just SNR. And that improvement is quadratic in the transmission bandwidth. So I increase the bandwidth, it depends on the modulation method. So I have to choose the right modulation method to get this. But I can get quadratic improvement in noise immunity. For the digital case, I'm looking at probability of symbol error, which we know is a Q function of SNR. So if my analog transmission is quadratic, my Q function will give me probability of symbol that gives me basically exponential improvement. And this is important because I had a student 10 years ago get all panicked that digital communications was dead and everything would be analog for the rest of his career, and he's wasting his time learning digital. The answer is both are important, and here's why. When you can sample fast enough, yeah, we'll go digital. But sometimes we can't sample fast enough. We got to go analog. And for some really low power applications, we might go analog. Both are useful. Okay. Thank you for staying over, and have a good weekend.